Hello, everybody. Welcome to the weekly colloquium series of the C3.ai Digital Transformation Institute. As probably many of you know, we are a consortium of universities and industries aimed at bringing together researchers who work on AI, machine learning, and cloud computing to the benefit of society. We have a number of industry and academic partners. So the academic partners are Carnegie Mellon University, KTH, MIT, Princeton, Stanford, Berkeley, University of Chicago, and University of Illinois, Urbana-Champaign. Our high performance computing support is provided by the Berkeley Lab and NCSA at Illinois. And our industry partners are C3.ai and Microsoft. I mean, they are the C3.ai gave a generous grant that allowed us to start the institute, and Microsoft provides the cloud computing support. In addition to them, we have AstraZeneca, Baker Hughes, and Shell as other industry partners. Okay, so we have a number of upcoming events, a number of upcoming colloquia. The next one is by Ishai Menachie at Microsoft Research, and then Murat Irchak at Berkeley, John Doyle from Caltech, Sanjay Shakotai from UT Austin, Wei Liu, and then Kaiyu Guan. So are the ones scheduled for the rest of the semester. In addition to the weekly colloquia, we also have other events. So we have a workshop coming up between September 22nd and September 24th, roughly 3 hours a day. So this is called Networks of Machine Learning for Machine Learning and by Machine Learning. So all kinds of interesting research problems at the intersection of networks and machine learning will be discussed here. And there is a digital transformation of the built environment workshop following that in October. So this is about smart buildings and smart cities and so on. All of our events are recorded and archived on YouTube. So if you miss an event, then you can always go to our YouTube page and then you can watch them later. So before I introduce today's talk and speaker, I just wanted to give you an idea of the format. So roughly the presentation will be 40 to 45 minutes, followed by questions, and you can use the Q&A feature to ask questions, and you can upvote a question if you'd like, and we'll try to ask the questions that have the most upvotes, and we'll try to answer as many questions as time permits. So the title of today's talk is Causal Tensor Estimation, and we have an outstanding researcher who will be giving this talk is Professor Devavrat Shah in the Department of Electrical Engineering and Computer Science at MIT. I've known Devavrat for a long time, and he has worked in many areas. I think of him as a probabilist and network theorist, and his current research interests are at the interface of statistical inference and social data processing. He has received many major best paper awards in many areas, including machine learning, operations research, and computer science, as well as major career prizes such as the 2010 Erlang Prize from the Applied Probability Society and the 2008 ACM Sigmetrics Rising Star Award. He's a distinguished alumnus of IIT Bombay. He co-founded a company called Select, which was acquired by Nike in 2013, and it helps retailers decide what to put where by accurately predicting demand using omni-channel data. So Devavrat, take it away.
Thank you, Shrikant. Thank you for inviting me to speak here. It's a distinct pleasure. Let me make sure that my slides are projecting right. As Shrikant mentioned, I try to keep my presentation to 40 to 45 minutes. Of course, please use the Q&A facility to ask questions, and I'll try to sort of see if I can monitor as I go along. And if there are questions that are coming up that make sense to answer, I will try to answer them. Otherwise, we'll follow, of course, we'll follow in addition the protocols Shrikant suggested. So this is primarily based on theses of two of my students, Anish Agarwal and Dennis Shen. Dennis recently graduated and now doing a postdoc at Berkeley with as a part of FORTC program, NSF FORTC program with Pengzhi, Binyu, and Just Sekon. And Anish is a PhD student who will be hopefully graduating soon. a good amount of work that I will present today is part of this archive link. There's also a working paper with Anish, Dennis, and Alberto. It's called Causal Tensor Estimation, and hence the name of this presentation. Also, I would like to acknowledge various collaborations that I will present in this talk with Abdullah Al-Omar, who is a grad student at MIT, Vishal Mishra, who is a collaborator and a faculty member at Columbia University, and Arnab Sarkar, who is another graduate student at MIT. All right, so here is the outline of the talk. What I want to do is I want to quickly walk through two scenarios that motivate the primary method and primary problem formulation that I'm going to talk about in today's talk, the method being synthetic intervention and the problem being causal tensor estimation. And the two scenarios would be one where we're trying to design randomized controlled trial in a data efficient manner. And I'll tell you what I mean by that. And the second one is evaluating policy. So the first one is more traditional randomized experimental setting where still there is a room to improve using method of causal inference. And second one is causal inference with purely observational data where it's very hard to obtain counterfactual or there's no possibility of doing experiments. And those are the two cases where I will briefly describe the scenarios and outcome, and then hopefully that will motivate you for the rest of the talk to go through the method. I'll try to give you the intuition and quickly the method. Depending on time, we may be able to go through the formal results or not, and then discussion and question and answers. So with that, let's get started. So here is a case study, a scenario that I'm going to describe that was inspired by trying to understand how to do precision medicine. And this is where one natural question of randomized controlled trial, but designed in an efficient manner comes around. It's in collaboration, of course, with Anish Agarwal, Vishal Mishra, and Dennis Shen. And also we worked with a pharmaceutical company who was kind enough to trust us with bringing our method. So they shared extremely valuable their clinical trials data with us. Right now it's anonymized because we're going through certain processes and hopefully a manuscript describing that, this case study would come out in a couple of months. So what was the setting? At the highest level, you're trying to do what I would call design clinical trials for personalized treatment. And here is just a high-level view of the setting. So there were 4 possible treatments in this setting. There were 3 drugs, and one of them was placebo. In addition to one was that placebo, so that's how 4. And there were patients. Now, patients came with different biomarkers, so to speak. And just based on these biomarkers, not clinical data, just biomarkers, patients were grouped into 6 subgroups or 6 types. So in an ideal world, if we wanted to do, I think my mouse is acting a little weirdly. So in the ideal world, if we wanted to understand which of these drug is the best for each of the 6 groups of the patient, we will have to do 6 times 4, which is 24 experiments for each patient type and each drug type or treatment type. We will have to recruit some number of patients at random, okay? And then ask them to go through this treatment and then sort of observe the clinical outcomes for them. And then compare across drugs for a given type. And then based on that, decide, well, for type 2, drug 1 makes sense, and maybe type 6 placebo is the best thing. You can't do anything, so forget about giving them treatment. Okay, so this would be a personalized setting. Now, as you may imagine, compared to doing this personalized setting, if we had just entire population and we were trying to do figure out which of the 4 things are good, it's like instead of doing 24 experiments, now you're doing 4. So that means that from a clinical trials perspective, this is 6 times cheaper. And if, as you may know, each clinical trial costs on the order of hundreds of millions, so especially at its stages. So this is a pretty expensive setting, and hence anything you can save in terms of data is worth it. Also, some of these diseases are really rare. So actually recruiting patients is very hard. So if you wanted to do recruitment, you might have to wait much longer in terms of time for these things to conclude than the amount of time it takes to recruit fewer patients. So for many reasons, it makes sense that you want to achieve these kind of outcomes, that is, achieve sort of personalized clinical trial design, but at the cost of population level clinical trial. And that's the type of question we are asking. So making it more precise, instead of running these 24 experiments or D times N experiment, what we want to do is we want to run these 12 experiments. In particular, all the places where there's a check, I want to actually run an experiment, and all the blank spots I want to fill up somehow. More generally, even if that D might not be 4, but much larger, I always want to have 2 times N experiments run. And what the method that I would describe in detail in this talk that will allow you to obtain counterfactuals for all possible experiments by effectively the cost of 2 times what you would have done in just a standard population level setting. All right, just at the quick glance of the outcome of the method applied to this setting. Here is what I'm showing you. What happens to a patient named like this when that patient's certain clinical measurements normalized is measured over 5 different visits over 18-month period. The blues are true observation. Our method had no observation. It only had information about the patient's biomarkers before patient started the treatment. And the yellow is prediction of the method, and it's entirely out of sample. And as you can see, and then of course, this yellow bar is the confidence interval that we generate around it. And as you can see, though each of these patients are coming under from the same type of group and same treatment, the outcomes are very different. But for each of those different settings, we are able to do a pretty reasonable counterfactual estimation. So that means that for individual patient trajectories and their clinical outcomes, you can forecast what happens or predict. Here's something more interesting happens. Once you have these individual patient trajectories, we can put things together. And as it happens in these clinical trials, many patients do drop out. They drop out for logistical reasons because they were enrolled in trial in a certain way, and for logistical reasons, they had to physically move to certain other places because of care and whatnot. And in which case they drop out. And these are like random dropouts, as they're not because of what they're observing. On the other hand, sometimes, especially when you have things like placebos, you expect that things should work, and now you're getting placebos, so you may feel that, but you don't know, of course, in the blind setting. But if the treatment is not helping you improve, you might say, you know what, this is not good. I don't want to sort of be enrolled and then you drop out. And indeed, what we did is, given we could predict what happens to each individual trajectory, we tried to understand what is the impact of dropouts on patients that were in the treatment. And as you can see, it seems like in treatment, patients were randomly dropping out. Again, we don't know ground truth here. The blue is the effect of change of score for patients. And this is like the blue is the distribution over them, all the patients who stayed through entire treatment. And the red is the curve for dropouts. And again, they seem like they're hugging each other. So most likely there's a random effect. On the other end, for placebo, there's a distinct bias that you can see between the patients who stayed in the treatment and patients who dropped out. Again, one thing I want to point out here is that the way this clinical measurement is done, higher this change varsity. So really, what you want is, if a patient is enrolled in the treatment, you want it to be closer to 0 rather than more than 0. And ideally, it would be less than 0. Okay. So this is one thing you could do. That is, you can sort of actually say, well, here is what dropout would look like. And this suggests that while if you ignore dropouts, the placebo and effect of treatment is very close. Treatment is a little better, but very close, but variance is very high. On the other end, if you start including dropout, suddenly there's much starker difference between those two things. Okay. And then finally, just coming to the population level, trying to understand what happens for each of those white cells in terms of prediction accuracy, as well as patient types, other than one exception for treatment 1 for patient type 3. For everything else, we have the R square is 80.8 or more. And that seemed to suggest that maybe the method is doing well. Okay. So that's a first case study. And the question is, so how did we do that? Is how did we impute, so to speak, patient trajectories, as well as the subpopulation level outcomes for outcomes for 24 trials by using only data of 12 trials. And I'll describe that in a bit. Second question is that of policy evaluation. So here, this is joint work with Anish, Abdullah, Arnab, and Dennis. All of them are at that time graduate student at MIT, and most of it was driven by Abdullah Alomar. Okay. And again, here the question that we were asking is that what would have happened to the United States if it had undergone different policy interventions in terms of social distancing, mobility restriction in the first 15 days. Okay. What I'm showing here is a plot of first 35 days, where 0 is indexed by the day on which 80th death in the United States was reported, now close to 18 months ago. And this is the number of deaths. And as you can see, my scale has 4,000, which means that we are 100x smaller, at least. And again, this was the initial part, first 15 days. And in those first 15 days, we hadn't understood anything about this pandemic. So really the only policy lever that was there was through different types of policies. At the end of the day, measured level was how do we restrict mobility of people so that we force people to isolate or distant from each other. Okay. We took the Google mobility data, and what we did is that we looked at the data available for roughly 20 odd countries. For those countries, we looked at what was the change in mobility aggregated at retail stores or retail locations and the transit locations. And what we found is that there's a group of countries which did not have much change in the first 15 days. There were a group of countries which had moderate change, and then there were a group of countries which had a pretty high change. There was these 3 clusters that were built. So we approximately say that there is 3 policy interventions happen: no restriction, moderate, and very high. Okay. So in a sense, we now divided possible interventions into 3 options: no restrictions, moderate restrictions, and high restrictions. And of course, for each country, we saw outcomes under one or the other, but the goal was to understand if we can predict for each country under each possible outcomes. Okay. Putting it another way, for United States, while we observed in first 15 days what happened to morbidity or deaths under effectively no mobility restriction, what would have happened if United States had imposed different policies, in particular moderate or high. Okay. And again, I'll describe the method in a second. But when we applied that to the United States, effectively we are using data for United States up to day 0. So data about United States in terms of their death trajectory up to day 0, and all the other countries, their data for first 35 days, including first 20 days till day 0 and the 15 days. And of course, with the knowledge that those countries went through one or another policy. So for United States, these dashed lines are the 3 different counterfactual predictions we do. What happens under low mobility restriction, moderate, and severe. And then on top of that, I'm plotting the dark line, which is sort of showing the reality. And given the proximity of these two, it seemed to suggest that we are doing something right. Okay. Similarly, we can do the same thing for United Kingdom. And again, United Kingdom went through true policy was low mobility restriction, and this is how counterfactuals look like. For countries that went initially through moderate mobility restriction, this is how counterfactuals look like. And then finally, for countries that through severe mobility restriction, this is how counterfactual looks like. Again, this was for first 15 days when the only lever was mobility restriction, and hence this was. Now, of course, one may ask natural question, what happens afterwards? Countries went through different policy changes, so there was a variation in it. And then more policies were imposed than just mobility restriction. Now, for example, vaccination and whatnot. So it has gotten, the landscape has gotten very complicated, and hence, indeed, application of methods that I'm going to describe is not going to be as straightforward. But in a sense, that actually is really exciting because we have data now for last 18 months. And in my mind, this is a nice test bed that has been created. So one should actually try to take some of the things I'm going to say today, which only applies really well for first 15-day style scenario, but then sort of apply to setting where these things are very dynamic and time varying, and there's a control that's applied. All right, so with that, I'll describe you two scenarios. One where it is just classical randomized control trial where, complications from causal inference are limited, but still data efficiency can help. This is a setting where data is fundamentally observed data, and hence counterfactuals are very hard. For example, the policy that was imposed in United States under which we saw the outcome, that has something to do with the characteristics of United States, in particular government and the population or people, okay? But that characteristic also determines the outcome in terms of COVID, the morbidity. So outcomes and the intervention have something to do with each other. So really it's very complicated. So how do we deal with this, these dependencies, and then somehow debias these dependencies to obtain counterfactuals such as this? So I'll talk about that next. And to do that, I will introduce this framework of causal estimation. Now I see that there is something in chat, so let me quickly look at what's there in the chat. And I think that sort of this is just a Larry's note for everyone. So let me continue. So I see that I have 25 minutes, maybe 20 more minutes to go before I pause for Q&A. So this is a framework of causal tensor estimation associated with the title. And so let me sort of parse through what is causal, what is tensor, and what is the estimation. This is joint work with Alberto, Anish, and Dennis, and this is a general framework that's that we are trying to put together in a forthcoming working paper. So let's go back to the causal inference, and one of the most generic way to think about causal inference is as simple as it gets, that is potential outcome framework. So what is potential outcome framework? In the context of the last case study we discussed, in particular for United States, under 3 possible interventions, there is low mobility restriction, moderate mobility restriction, and high mobility restriction. You say, well, there are 3 different distributions that are out there. Distribution that United States would reveal under one policy versus another policy, another policy. Okay, and this is an oracle view. We don't know what they are. In reality, what happens is one of the policies is observed. Okay, and for one of those policies, when it's observed, we observe the outcome. Now, in principle, if we forgetting the distribution, let's just say expectation of those outcomes is what we want to estimate. Okay, and really, we want to estimate that for all potential outcomes. Now, the challenge or the problem is that these D star that has been observed has something to do with the distribution that we've observed to. So there is some correlation that has happened, and that might distort our observations itself. Okay, and that's basically what makes it challenging. And I'll sort of parse through this as I go forward in the next few slides. Okay, so just to summarize, the fundamental question of causal inference is, for all possible D or interventions, I want to find out what these potential outcomes are. Again, if I could do experiment, that is, I could go and sample, I have 3 United States, and I can run experiment, well, United States 1 that is under low, 2 under moderate, 3 under high, and sample things out from there without creating any dependencies, then that's a solved problem, and there is nothing really difficult about it. Okay, what is really difficult about it is that we usually observe outcomes only under one setting. Even in case of clinical trial setting, we observe given patient's outcome under only one setting. Maybe population level, we may observe multiple outcomes. In context of United States, we observe outcome only under one United States, under one policy. And there is a dependency, or as the causal inference world would like to call it, confounding. Okay, so let's understand what is first confounding. Okay, and again, if you have known this, this is almost a silly example. And if you have not, then hopefully this will help you just get to know what the word means. Okay, so imagine a scenario where you have 2 drugs, A and B, and imagine this is a world in which the effect of drug is classified only depend on the gender. Okay, and higher the number, the better it is. So when drug A is applied to given to men, its efficacy is 10. Drug B is applied to men, its efficacy is 20. And when the drug A or drug B is applied to women, efficacy is 0. Okay. Now, in the randomized setting, what we would say is that, let's say the world has half men and half women. 50 of them get A, 50 of them get B, and vice versa. And then if we measure average treatment effect, let's say, well, 20 plus 0 divided by 2, B is effective is 10 versus A is effective as 5. And then we will say that, well, if we are going to decide on a situation where only one drug can be applied, and we are not going to sort of personalize it, then we'll go with B as a population level. On the other hand, if I want to game the system, and if I knew these outcomes, I would say, well, if a person is men gets A, and if a person is woman gets B, then what I would find out is that all the people who have gotten A, their efficacy is 10 units versus for B, efficacy is 0. So of course, A is better. And clearly you see that there is something wrong that has happened here because I confounded my selection. Okay, that's basically confounding, and that's why it's a problem. Putting a little bit more structure around it, one way to think about, again, at the high level, there's an outcome that is of your interest. There is some characteristics of individuals getting the treatment, characteristics of a context. So for example, context could be situation, the temporal context, such as temporal context in the United States, or temporal context in any other country. And then there's a characteristics of United States or characteristics of patient, like in previous example, gender. These are let's call it confounders, which could or may not determine what intervention that is given. And that, along with your characteristic, might determine your outcome. Okay? So this is a very generic way of thinking about typical causal inference problem. Okay, this is my DAG, and I'm drawing it dashed here because maybe the assignment that has happened, or intervention or treatment that has happened, may depend on confounder or may not depend on confounder. If it's randomized control, treatment is independent of confounder. If it's setting as I confounded in the previous example, then there is definitely a dependence. There's definitely a dependence in terms of the policy applied to United States in first 15 days that led to outcome in terms of the morbidity or deaths. Putting it in a simple functional form, and again, I'm ignoring a lot of stochasticity here, but the random variable y is some function of a and u. And maybe a is some function of u. And again, if a is assigned randomly, then this function is null, and maybe there's some random. All right. Now, given this, what counterfactual prediction says is that given my treatment choice, for a population level, where population level says distribution of these confounders or contexts or both, I want to evaluate y where f of a given u. So it's a distribution over population, or maybe it's average that might be of interest. At individual level, that specific individual, that specific context corresponds to some realization of u, and I want to evaluate outcome there. Again, there may be randomness, and in that case, I'm looking at the expectation. So this is my individual level counterfactual prediction. This is my population level counterfactual prediction in this simple setup. And really, when you do randomized control trial, for every year, you're sampling sort of individuals at random from population, and hence you're actually getting samples from this distribution, and hence it's feasible. But of course, you won't be able to do that at the individual level because one individual is given only one of the treatments. More generally, the challenge that is there is for a given context, we don't observe outcome for all A's, okay? And the data from which we want to learn something about the structure, U and A could be correlated, could be dependent, and that makes it really hard to learn the relationship that you want to learn. And more generally, U at best, the context of interest confounder, at best is partially observed. Generally, in many of these studies, you would sort of posit that, hey, I think these are the covariates, these are the confounders that matter for me to determine the outcome. But in reality, they're unknown, they're latent. So how do we do this? How do we learn this? And how do we do this without knowing F? How do we make these predictions? Okay, and what I want to do next is provide a framework under which we could do this. Could do this formally, and we could do this using simple method. And that's exactly what we did for those two case studies that I showed you in the beginning of talk. So in remaining 12 to 14 minutes, let's see if I can sort of go through the framework and at least intuition behind the method. Okay, so the way we are going to address this problem is by looking at an alternative representation, the tensor. So again, causal tensor estimation, I described you what the causal question is. Now I'll want to describe you how the tensors come into play, and then we'll describe the estimation part. So again, this is just a simple translation of available information. Here I'm showing 3 slices or D slices. Think of each slice as outcomes of different units, such as in the first case, patients or patient types. In the second case, different countries. So these are units. These are different measurements. In the first case, it was measurements over patient visits. In the second case, it was measurements, daily death count measurement. And then different slices correspond to different intervention. In the first case, it was different treatments, placebo or treatment one or so on. In the second case, it was different policy, low mobility restriction, moderate mobility restriction, high mobility restriction. And really, it's this information in these slices is what matters. And let's think of these as, for example, in the second case, it could be death outcome for United States on day T if nothing was done. There is low mobility restriction. Or same row, same column, but different slice, it would be under some blue policy and what. Okay. So really estimate this tensor is of our interest. Okay. Just to sort of map this and asking the question in the context of first setup of clinical trial, a personalized treatment effect. Really, this is my ground truth tensor of interest. That is 5 visits of patient, 6 patient groups, and 4 different treatments. And if I could know all of these really well, then actually I've got all the answers I'm looking for. Of course, the observations are in this type of design are limited. So for example, under placebo, I have outcomes for all 6 types. And that's why I know entire gray slice. But for drug 1, I know outcome only for first 2 types. And that's why these 2 types are there. Here, I know only drug 2, I know only for type 2 and 3, and so on. So that means that I've got a tensor which is partially observed, and I want to fill it up. That's why it's a tensor estimation problem. So hopefully by this time I've parsed my title of the talk, 35 minutes in. Well, it's better than 45. And again, so this is a Zoom setting, so no interaction, but in a normal world, I would assume that hopefully there will be a laughter there. All right, so we want to estimate this tensor for each patient type and treatment over 5 visits using partial observation. Luckily, in this case, data that was available or assignment of treatment to patients was done independently because this was randomized setting, and hence there's no confounding. On the other hand, in the context of understanding the impact of policies on COVID-induced death outcome, the treatments were confounded, or observations and treatment were confounded. In particular, policy implemented in the country depended on characteristics of the country. And we still want to impute the tensor. And in that case, the tensor looked like this. There's a day 0 for all countries. Of course, the actual date might be different. That is, in the United States, day 0 might be March 15 versus in India, it might be April 1. But we aligned them by saying the day on which 80th death was reported. In that sense, these things are aligned. Before day 0, all countries had no mobility restrictions. Some countries had no mobility restriction after that, like United States. Some had moderate and some had high. And based on this, we want to fill up this missing values in this tensor. Okay? And that's what we want to do. So for both of these problems, it's a tensor estimation problem, but observations pattern could be different. And what things are observed and not observed, that could be dependent on the characteristics of the tensor itself. Okay. Now, for any tensor, as we know, one could, like matrix, one could write down a decomposition of tensor, like a CP decomposition, as we would call it. It may not be unique, it may not be succinct, but you can write this down. Okay. In particular, there are components associated with units, components associated with measurements, and components associated with interventions. The assumption that we're going to make in this framework, and this is the first assumption, is that the rank or number of components that really matter in this tensor are small and that don't scale with, for example, dimensions of the tensor. At least, and the dimensions of these tensor do scale, at least 2 of them, if not all 3. Okay, so for example, I might have lots of units and a lot of time, or lots of units and lots of interventions. But some of these things are scaling. Okay, so as a generative model, there are latent factors or features associated with unit, measurement or time, and intervention that are sampled. So they're given or sampled. The potential outcome, expected potential outcome tensor of my interest is this nice decomposition, low rank. Then I'm going to, for every unit and time, I'm going to decide what treatments will be available for them. For example, for a given unit and given time, only one treatment might be assigned, or a subset of treatments, or all of them for that matter. And that's why it's a subset of possible D treatments. And then finally, we observe outcome based on this simple model where there's a mean plus some noise, and noise distribution is 0 mean, and it's nice in the sense that it's a sub-Gaussian, and but per entry distribution could be arbitrary. Okay. Now, what about the joint distribution of this? That is, how are D decided and how is Y decided? Do they have anything to do with each other? So I'm going to sort of draw the DAG quickly and tell you sort of what is prohibited. That's another assumption. Okay, so there are latent factors, as we discussed, that are sampled. Latent factors may imply the distribution of noise that you observed for entries, and that will also impact the mean. because remember, latent factor determine the mean of the potential outcomes. Okay, so these are the dependencies. Latent factor may also determine, with arbitrary function, determine the interventions that are decided. Now, the only thing that's missing, to make it a generic distribution, I need to add this arrow, okay, or arrow from interventions to these distributions. What we would do is we would prevent this arrows for this idiosyncratic noise. Okay, this arrow is missing, and that's an important assumption. Okay, what does this do? Here's what it does. What it says is that, in general, this assignments of treatment and outcomes are not independent; they are dependent. However, if I condition on these latent factors, then they become independent. And in the traditional causal inference literature, when these factors are covariates that are known and observed, or confounders, and we call selection and covariates, or selection confounders. Here, since these are unobserved, we are going to call them selection on latent factors. Okay, so that's what how it fits into the causal inference literature. Given all this, of course, goal is to estimate the whole tensor as well as possible. So of course, the question is that under what scenarios can we do that? What are the observation patterns that will enable us? Of course, if everything is observed, then one should be able to do this. Question is that what are the restrictions that allow us to do it? And one such solution is synthetic intervention. So there's a general problem that I stated just a second ago, where when can we do estimation? That's not, I don't know answer to that general question, but here is a feasibility answer. Here are some conditions under which we know how to do that, and that's where the method comes in. So I know that I'm running very close to end of my time. If it's okay, I'll take maybe 5 more minutes and then conclude.
Yeah, that's no problem. Yeah.
Okay, thank you, Shrikant. Okay, so just to summarize what the goal is here, for units and different interventions, so n units and d interventions, we've got n times d causal parameters effectively. We think of average treatment over time or mobility, death restriction. And we want to estimate these n times d causal parameters with limited observations, and observations might be confounded. In particular, what we will argue is that through the type of experiment we designed for randomized control setting, as well as the observation pattern that we have in the policy evaluation setup, effectively we'll be able to impute n times d causal parameters with data that scales with n times 2. Okay, so that's a punchline. All right, what I'll do is I'll give you quick intuition of how this works, and maybe walk through at least a little bit more detail. So going back to that simplest setup that we were discussing, again, there's a confounder, there's an intervention and outcome. Okay, first of all, if we are observing, let's say intervention is a function of your context. We don't know that function, but there's a function of context. And let's say A takes 100 different values and U takes 100 different values, then we want 10,000 different data points really to understand function fully. Now, of course, if you have a generic function, there is no way to do that, because if A is a function of U, really, we are observing data at 100 tuples rather than 10,000 tuples. Okay, so we need some structure in the function, and one natural structure that would arise for many such functions is factorization. And this factorization is not really that much of a stringent assumption, because just the way we have singular value decomposition of matrices or tensor decomposition, this is what would enable imputation. That means even though we might learn things from limited data, we could actually extrapolate to the rest of the all observations. The second part is, well, okay, this might enable some imputation, but how do we do counterfactual estimation? Because we don't know what are the confounders. Well, in some sense, because of this high dimensional structure and multiple units and multiple observations, we're able to learn latent features of different units as a function of some other units latent features implicitly. And that allows us to do the estimation or counterfactual estimation. Let me put this operationally. Operationally, the idea is very simple. I want to estimate what happens to United States under severe mobility restriction. Well, I have observed United States only under mild mobility restriction, but hey, before day 0, United States and France looked very similar. And hey, France went through severe mobility restriction. France is exactly like United States. So let me just assume that what would have happened to United States is exactly what happened to France. And that's it. So simply, it's like nearest neighbor learning, or what one would call in world of recommendation system, collaborative filtering. That is, I find my similar other units from data that was available pre-COVID, and then use that learned relationship between them to extrapolate using the data for those few folks to extrapolate it. Okay, and that in a nutshell is the synthetic intervention method. And when we are learning this relationship, we are learning relationship between these characteristics or confounding associated with the units that determine maybe the policy itself under which they will be observed, as well as the characteristics that determine the outcomes. Okay, I'm not going to, due to time, I'm not going to go through precise details, but in the simplest world, when it was just understanding one understanding control setting, this was proposed by Abadie in the beginning of the century, around close to 2003, known as synthetic control. One way to think about synthetic intervention, the method that I'm suggesting, is a natural generalization of that to allow for all sorts of dependencies and go across different interventions. Okay, so with that, let me sort of let me respect the time and stop here. But what I would like to do is simply say that there is a nice formal results that allow you to build confidence interval. There's a data-driven hypothesis test so that when you are going to apply this method, you're reasonably confident that it's going to work or not. Okay, and if it doesn't work, I have no prescription of what to do, but at least I will tell you when it will work and when it will not work, because method is simple. And finally, for me personally, I came to this question because I was very much interested into the broadly question of matrix and tensor estimation. And from machine learning world, there's a huge activity in this space in machine learning world for last 2 decades that led to all sorts of exciting development in statistics, computation, complexity, and just practical impact of those things. In the causal inference world, this has come from panel data setting, as an econometrician would call it. And there's lots of interesting dialogue that needs to take place here, where computation in machine learning can say something about causal inference and the world of econometricians, and vice versa. And I really hope that some of these things would get us started towards that. So with that, let me stop and now take open questions.
Thank you, Devavrat. It was a great talk.
Thank you.
So if there are any questions from the audience, please post them in the Q&A. I have a question, so I'll start off with that. So I guess as you mentioned that it is somewhat like matrix completion, or except that this is a 3-dimensional quantity, it's a tensor. And you said that one way to complete the matrix is sort of through this nearest neighbor kind of ideas. To complete the tensor, I guess in the matrix completion world, I've seen 2 kinds of things, where one is this nearest neighbor thing and the other using spectral methods. Yeah. So is there a equivalent of that here too, where you sort of try to do a SVD kind of thing and then try to fill in the blanks? But then I guess the difficulty there is that what do you start off? What do you assume in the empty spaces? So is there an answer to that?
It's, first of all, brilliant question. Thank you. Great segue, great question. And I think, as always, Shrikant, you're thinking of 2 steps ahead of everyone. So let me catch up everyone. So I think just paraphrasing Shrikant's question well simply, right? Let's forget tensor and let's say you even go back to matrix, right? In machine learning world, in the matrix estimation or matrix completion, one would say that you have got a matrix with, let's say, low rank or approximately low rank structure, and you're observing a small fraction of data, but small fraction is sampled uniformly at random. Okay, and that's what there's a terminology that has evolved at the interface of matrix completion and causal inference. This would be MCAR, missing completely at random. Then there is a nice next variation of this that will arise, is not missing completely at random, but missing at random with some intensities. So for example, one model would be that an entry is missing with probability, so entry ij is missing with probability pij. So pij itself is a matrix. And this matrix is of some form of, let's say, also satisfies low rank. However, for each entry ij, in a sense, you first sample with probability pij, whether you observe or not, and then you observe or not. And it has nothing to do with another entry. Now, this is kind of an intermediate step, and there's lots of interesting work that has happened in this space. One of the earlier work that formalized this well is by paper by Ma and Chen, George Chen, who was at CMU in 2019, and they put out a few sets of algorithms and all that. And there's a nice variation of both spectral method as well as the optimization-based method that's suggested. Very recently, there's 2 groups of folks that have proposed a little bit sharper results around this. One is by Saurav Chatterjee and his collaborator from Stanford. It's, I think, came out in August this year, so it's like literally fresh out of press. And a group from Jacqueline Fan from Princeton, Orphe. And for these models, they have both analyzed spectral method, as Shrikant you suggested, as well as optimization based like Candace Rect style of estimator. And effectively, they established consistency results of certain form. And there, the idea is that, as you correctly pointed out, you have to replace zeros by something, for example, in spectral thing. But first they do is that they estimate the mask intensities, that is PIJs, and then estimate the true matrix and then take the ratios of those two. Okay, so there was that. Now, really more interesting question, maybe in this case, as I was saying, the D or the observations can be arbitrarily dependent on your latent factors. And in that case, what do you do? So in a sense, what we are solving here is we are saying that under certain patterns, you can actually solve it. And maybe now I'll shamelessly advertise something. Hopefully we'll put out an archive in a couple of weeks that Dennis, Anish, myself, and my colleague Munzir Dale, we are working on. It's a causal matrix estimation. So what are the general quotes and quotes observational patterns that allow you to recover that? And some of these nearest neighbor style algorithms, more complicated than what I just spoke, but nearest neighbor style algorithms actually allow you to not only estimate the entries, but also you can prove central limit theorems for them. So there is something interesting happening there. But again, I strongly believe that we haven't sort of exhausted that. There's a lot more to do there. So I feel that if there's one thing that I leave audience with this, causal matrix estimation and tensor estimation, it's a really interesting, hard problem. And one shouldn't think of that as it's just yet another variation on the theme that theme has been going for the last 20 years.
Awesome, thank you. Are there any other questions? I have one more question. I really enjoyed the talk. So the time series aspect of it, so you get as a function of time. So are they correlated or are they independent measurements?
Perfect. So in the model, they are correlated in means. That is, they might have dependencies, but they're deterministic means. So that's not really probabilistic correlation in that sense. But the noise part, the epsilons, are independent.
Okay.
So there's some structure, but that structure is not probabilistic dependence.
I see. But you could also imagine some form of correlation. For example, COVID, that's people learning something about the disease, and then so that might change what is happening. So that could be an additional component, right? Yeah.
It's a brilliant question. So one of the things we're trying to sort of formalize these kind of things with in the paper with Alberto on with the title of this talk is where we're trying to argue that there are factor models that not only capture this spatial relationship, but also temporal relationship, not just mean, but also higher order parameters of distribution. And then some of the things in the world of econometricians they call, and it's this beautiful actually type of data that's, where suppose, let's say, as we all go through doctors, right? Doctors assign us, let's say, certain pills, for example, for blood pressure, right? You are measured over time that whether your blood pressure is above or below certain band. But only after it crosses certain band, you are given a treatment and not before that. If you are above 65, you get Medicare, but below 65, you don't. So there are these interesting characteristics of individuals or unit which determine whether they get certain treatment or not. Okay. These are, in that world, are studied under regression discontinuity umbrella term. Our point is that these things naturally incorporate those things as well, and hence provide a lot more than what's already studied in that space, where in regression discontinuity, it's all about studying impact or understanding of treatment effect around, let's say, around age 65. If people are around age 65, is 65 better or 65 minus 6 months or 65 plus 6 months? Those are the questions you can answer. But for these, if you have some variation, you can actually do across entire age and spectrum. So I feel that there are interesting things that some of the interesting things I know, but I think there's a lot more interesting things that needs to be done. Like how do we do controlled dynamical system in this framework? Mm-hmm. I think it's a really hard, and I don't know how to answer that question. And it would be great if some of us who like dynamical systems start thinking about that.
Awesome. Thank you very much. So I think there are no more questions. So thank you again. It was a great talk. Learned a lot, and I'm sure everybody did. Bye.
Thank you. Thank you, Shrikant. Thank you for hosting me. Bye-bye.
Welcome. Bye.